I'm Doug Beardsley. I work at a company called Kadena in New York, and I'm here to talk about our smart contract language called Pact, and how Pact can help you write smart contracts that are less likely to have bugs and more likely to do what you want them to do. Quick overview of what we're going to cover. Start with just a little bit of a high-level blockchain background, whirlwind overview. I know everyone probably knows it, but just to establish a baseline of what we're going to be talking about. Then look at some of the problems with smart contracts. We're not going to try to enumerate all of the problems, but just a few that I think are important. And then look at how Pact solves these problems. So what are blockchains? They're, at their core, tamper-proof, append-only digital storage. Now, we've had append-only digital storage for a long time, and the core thing that blockchains add that we did not have before is that they allow us to make these stores tamper-proof, which is really a pretty significant thing, and I think the world is still realizing and coming to appreciate exactly what the significance is. Blockchains accomplish this by storing the same data on lots of different computers around the internet. Every one of these computers that is participating in the network has to agree exactly on the data in this store, and that's what we call consensus. The result is that you don't have to trust a central source of truth. The network is your source of truth. Now, smart contracts. They're a little bit of a misnomer. They're not really smart, and they're not really contracts. They're just computer programs that you store on a blockchain. And they are run by the computers that are participating in the network that is storing the blockchain data. And that's kind of all they are. But writing programs in this domain is different than writing programs normally, like most of us are used to. Every operation that you do, it has to be run on thousands of computers across the network, which is not normal for us programmers. And every one of those computers has to have exactly the same results every time. The same inputs must always give exactly the same outputs. If you don't have that characteristic, then you can't establish consensus. And the baseline of what we use to determine whether something has been tampered with is gone. And that's really different than normal. Most programming languages have functions that will say, get the current time. But the current time function returns a different thing every time you call it. Or it may be something else that reads from the keyboard, and it returns whatever key you press, which is not necessarily always the same. If you run that in a blockchain context, you're not going to get the same result, and you won't be able to establish consensus. And this is a really significant point. Another thing is that since these smart contracts are often dealing with cryptocurrencies, various kinds of digital representations of assets, the stakes are a lot higher than normal. And there's lots of digital money on the line, and that is a new thing, I think. Also, you have to pay transaction fees, maybe not in all blockchain settings, but certainly the popular ones. In order to interact with any of these smart contracts, you have to pay some fees. It just adds another layer of difficulty that you want to make sure you're getting things right. And then because these stores are tamper-proof, the code that you put in them is immortalized forever. It's there, and you can't go back and say, oh, I need to fix this thing. You could potentially release a new version of that thing, but the old version is still going to be there, and there's nothing you can do about it once you put it out there. And that's also fairly different from what we are used to. The result of all of these factors is that correctness in a blockchain context is much more important than usual. So what is the problem? Bugs. Smart contracts are notoriously buggy. 25% plus of contracts tested in this one paper had exception vulnerabilities. And this is just one kind of vulnerability. And there's plenty others. I'm not going to try to characterize like the total percentage of buggy contracts. But whatever it is, I think everyone agrees that it's a lot. What does this do to us? If you have contracts that are buggy, people are going to be less likely to put their money behind them. And that means that the adoption is going to be slower. So higher risk, slower adoption, that's not what we want. This is a new technology. We want to experiment with it. We want to allow people to have reduced risk and adopt more quickly so we can learn faster. So what are some problems with smart contract languages? Well, there are a number of them. I'm not going to try to enumerate all of them here, but I want to focus on 3. First of all, they're based on mainstream languages, or at least a number of them are. Second, code that is stored in the blockchain is not human readable. Certainly in the case of Ethereum, you're storing EVM bytecode, which is not the thing that the programmers actually work with, but that's the thing that is immortalized in the blockchain, and that makes it harder to understand what's going on. And then these languages are often difficult to verify and be confident that they do what you think they do. So let's look at these in a little bit more detail. A while back, there was a smart contract called Rubixi. And this is actual code for an actual contract in the Ethereum blockchain now. And it's not obvious what happened here, but on line 13, we have this function, dynamic pyramid, which was the old name of this smart contract. But then somewhere along the line, they decided that they were going to rename it, and they renamed it Rubixi. But they forgot to change the name of the constructor function. What that does is it means that that function, dynamic pyramid, is not a constructor function anymore. And that constructor function is the function that sets who owns this smart contract. Big problem. Anyone can become the owner now, because that's not the constructor, that's just a normal function that anyone can call. And so it basically made this completely a free-for-all. Anyone in this room can go and submit a call to this dynamic pyramid function, and then you will become the owner of the Rubixi contract. Well, what that probably means is that not very many people are going to use Rubixi anymore. But I thought this was a really interesting illustrative example. The object-oriented paradigm and the associated DRY violation. Now, DRY stands for don't repeat yourself, which is a common best practice in software. If you repeat yourself and you change one thing and you forget to change the other thing, that can often be a bug. And that's exactly what we had in this case. And the object-oriented programming paradigm that says, oh, we're going to have a class and the constructor of the class is going to be the same name of the class is directly responsible for this bug. So mainstream languages, I argue, are not sufficient for smart contracts. This Rubixi problem, you wouldn't think that this was a significant thing in OO languages. It's just a 2-minute fix. You're like, oh, I forgot to change the constructor name. You change it and you move on. But in the smart contract setting, you can't change it because it's tamper-proof. And that is a really big issue for a lot of contracts. Also, mainstream languages aren't very good at guaranteeing determinism because we've never needed that before. It's fine to have a function return a different value every time. We need it all the time. But in this setting, we can't have that. And so we need languages that understand this and have this taken into account from day one when the language is being designed. And third, mainstream languages just don't provide enough safety for this high-stakes environment that we have in the blockchain world. Second point is code is unreadable in the blockchain. Now, the counter argument to this is that, oh, you can publish your code, and then people can verify that that code created the EVM bytecode. And that's true, and it's used, but only about 1% of contracts have their source code available. So clearly it's not very widespread, and wouldn't it be better if we were building on a system where you just were putting the human readable stuff into the blockchain from the get-go? And my last point, these languages are hard to verify. There are situations where fallback functions in Solidity complicate the control flow. Values can be mutated. Mutation is a little bit harder to analyze. And a lot of these languages are Turing complete, and that makes them much more difficult to analyze. So, how does Pact address these problems? Well, first of all, we did not default to a flawed paradigm just because it's popular. We said, let's really think about what characteristics we need in our language in order to make the guarantees that we want achievable. Pact is purpose-built with smart contracts in mind. The code in the blockchain is human readable. You will put Pact code right into the blockchain, and everyone will know exactly what code you were looking at when you wrote it. Also, we are going to have a provision for smart contracts to be updated or fixed. This does not revert what I said earlier about blockchains being tamper-proof. We're going to have a mechanism for declaring a new version of something. And people will just, by default, use the new version, and that's a really important feature in a lot of situations. It's also designed for storing data, which is really one of the key things that blockchain programs do. It has built-in auth infrastructure, which is often a source of trouble. And there's all kinds of things that you can get wrong if you're rolling your own crypto. So we're putting that in and taking care of most of those concerns for you, so you can focus on the business logic. You also can't put encryption keys in code. Currently, this is fairly widely considered a best practice, but you can still do it. In Pact, you can't. It just can't be done. Also, Pact is not Turing complete. Values are immutable. And it's an open source language. It's written in Haskell by people who are familiar with cutting edge programming languages. Haskell is fairly widely understood to be one of the bleeding edge languages where a lot of programming language research happens. And the people that built Pact are aware of this stuff and are able to take the state-of-the-art technology in programming languages and apply it to the blockchain setting. So here's a little example of what some Pact code looks like. On line 1, you can see we're defining our admin key set. And you can see this read key set call here is where we don't allow keys to actually be put into your code. You have to call this read key set function, and the key comes in from outside of your code. Then you associate this key with this module, so that key is the key that has the admin privileges for this module. And it's just very straightforward. There's nothing complicated. You're kind of saying what you want. I'm not going to talk about most of the rest of the code in detail, but I will point out that down here at the bottom, lines 22 through 25, this is where the constructor code goes, and it doesn't have a name. That name doesn't have to match the name of the module. It just gets run by default, so the problem that Rubixi had cannot possibly happen in Pact. Also, Pact has formal verification. Now, a lot of people throw around the terms formal verification, and I think it's not really appreciated quite what's going on. Formal verification, at least in Pact, allows you to prove things about your program for all possible inputs. It would be impossible to actually test them all. What we're doing is we're doing math to analyze the way the program is structured and actually have a proof that certain conditions can or can't happen. And that's really, really powerful. And it's benefited substantially because Pact is not Turing complete. It becomes much more easy to analyze. So here's a little example of formal verification. This is a very simple function. It calculates the absolute value. It just takes one input, an integer, and returns you an integer that is the absolute value. And there are a number of things we might want to prove about this function. We might want to prove that the result is always greater than or equal to 0. And this is exactly how you would do that. You just say that there's a property that has to be fulfilled, that the result is greater than or equal to 0. And Pact will actually prove that for you. This is something that it can do, and it works today. Another really interesting one are these two about not reading or not writing to the accounts table. In some circles, they call this side effects, and you often take them for granted, but we can prove these things in Pact. We can prove that this function does not read or write from any database table. And for simple functions like this, that's really useful. It would be really problematic if this program did read from the database. But the language would allow it, but we have this property checker that can make sure that you're not doing that. It doesn't seem as significant for a small function like this, but when your functions get larger, it's really easy to lose track of what was happening somewhere down further in the code and not remember that this property had to hold. So, just to recap things, humans are always going to mess things up. I think that's a pretty clear takeaway that I've had in my software career. When we look at all the bugs in smart contracts, especially like this Rubixy one, that was a bug that is easy and obvious. It's not subtle at all, but there are just so many details that you have to wrangle when you're writing software that you're not going to make sure they all line up. And so I think we have to accept this as a fact and try to build systems that make these kinds of mistakes actually impossible, so they cannot happen. And because the stakes are higher in the smart contract domain, it becomes even more important that we do this. Pact was purpose-built, designed just for the needs of writing smart contracts. It's human readable, and it has really great formal verification properties. And check it out. If you would like more info, I'm going to be around. You can certainly talk to me here. We have some documentation on our website. You can also try Pact just instantly by going to the try Pact page, and you can play around writing a little bit of Pact code right there. Pact is also open source. You can look at the code. It's on GitHub. You can give us pull requests and open issues and help us evolve the language. And also, Kadena is hiring. If you are a Haskell developer and you would like to work on this language, then definitely send me your resume. Also, if you're not a Haskell developer, we are going to be looking for people who can write Pact code for clients. And so there are job openings there as well. Thank you very much. Oh, I guess we have a little time, so are there any questions?
So we'll ask you to speak to the microphone, so our volunteer will bring the mic to you. Please wait until, raise your hand and wait until he brings the mic. So thank you, Doug. This is awesome. I want to thank you from the bottom of my heart for bringing Lisp code to the old Bourse of Amsterdam. This is probably the first time when it happened, and you're a Haskell company, so it's all very near and dear to me. Question: I mean, it still looks complicated, right? So when you talk about Pact developers, so how do you envision enterprises who still use COBOL in their basements and Excel and things like that. How do you envision, how much harder is, say, Pact than an Excel function in reality? How do you envision the development environment? Will there be an IDE? Will there be Pact meetups and people sharing tips? Like, how do you envision the ecosystem, and how do you envision this? Are these people going to be developers? Are they going to be business users? If you can talk to that.
Yeah, I think that Pact is actually very easy in some axes because the syntax is incredibly simple. It is a Lisp, as Alexei mentioned, and other people might have noticed. So the syntax is very, very simple, straightforward. There's not a lot to learn there as far as syntax goes. As far as IDE features and like larger scale development, we definitely foresee those kinds of things happening. The Lisp community already has a fair amount of tooling. We'll try to steal as much of that as we can and make it our own. I absolutely envision meetups and thriving developer communities, but these things take time, and we just need people trying it out, using it for their problems, and seeing what works and what doesn't. Any other questions? Right here.
Yeah, very interesting talk, thank you. I'm minded that there's been a lot of work in verification, and certain vertical sectors are very strong on it. For example, if I'm writing software for an aeroplane, I probably go. And I'm wondering, to what extent have you been able to leverage learnings from those areas?
So I can't speak for specific domains, but under the hood, Pact uses the Z3 theorem prover from Microsoft. So we are absolutely standing on the shoulders of giants there. And that's what really makes all of this stuff go under the hood. Other questions? Over here on the right.
Is it possible to roll random numbers? Because there are algorithms like Quicksort which use random numbers but are still deterministic.
Great question. No, because fundamentally that is not deterministic. So if you're going to do random number generation, you have to do pseudo-random number generation. Take the cryptographic hash and take some bits of that. You could implement your own pseudo-random number generator and then pass in the seed as an argument to the function. But that is an area that I think makes my point that smart contract programming is very different. Because normally we just take for granted that we can, get a random number from anywhere. But you actually have to be much more roundabout. You can't just do that in smart contracts in general, because every computer out there will run the program, get a different number, and now no one will agree on consensus. And that just doesn't work in this setting. Any other questions? Thank you very much. I appreciate the time.